One of the successes of the periodic table is how it organizes elements into groups. Vertical columns of elements all share the same number of valence electrons and as a result exhibit similar physical properties and similar trends in reactivity. As an example of this, we'll look at some elements in column 1A, the alkali metals. In this demo, we're going to look at the reactivity of lithium, sodium, and potassium. However, other groups in the periodic table have similar reactivity trends. Alkali metals all have one weakly bound electron and are highly reactive. When alkali metals come into contact with water, they react violently to form hydrogen gas and a hydroxide. Moving down the group, there is an increase in reactivity, illustrating a periodic trend. Alkali metals react so violently with water that it can actually pull water out of the air and react with it if you leave it sitting out. So typically this is stored under mineral oil, kerosene, or something else. This lithium here had a little bit of oxide that had formed on the surface, so I scraped it off with a knife and then cut it into a small piece and placed it into toluene for use later. This sodium is a little bit fresher than the lithium, so when I took it out there was already a pretty clean face, as you can see there. It's pretty shiny. I cut it with a knife. This is actually a very soft metal, so you don't actually even need a knife, but cut it down to a size that was appropriate for this demo. The potassium looks a lot like the lithium and sodium, and I did the same thing here, cutting it into a smaller piece and placing it into toluene for later. After cutting, I have 3 similarly sized samples of lithium, sodium, and potassium in toluene. To show that this reaction produces hydroxides as a product, I'm adding a little bit of phenolphthalein to each of these beakers. Phenolphthalein is a pH indicator that turns pink at basic solutions when the pH is higher than 7. Watch what happens when lithium is added to water. If you listen closely, you can hear a fizzing from the hydrogen being generated from the reaction, and you'll see that lithium is floating on top of the water, bubbling, there's some steam rising up from the heat, and the solution is slowly turning pink as it turns basic. Let's watch this reaction again from a slightly different angle. You might notice that while this reaction is vigorous, it's a little bit slow. The reactivity of alkali metals increase as you move down the column, a periodic trend. Sodium is lower on the periodic table than lithium, and its valence electron isn't held onto as strongly. You can see that it's more reactive, and when it comes into contact with water, it generates so much heat that it actually melts. You can see that it's formed a bead as it's rolling around here on the surface. even though sodium reacts more quickly with water, this bead seems to stick around a little bit longer because it's generating so much hydrogen gas, it actually lifts itself up off of the water and doesn't come into contact fully, as lithium did. This is similar to the Leidenfrost effect, which is what happens when you put a drop of water onto a hot pan. It evaporates so quickly that it creates a little cushion of air and floats. Potassium is clearly the most reactive of the three. Even though it melts and floats like sodium, it generates enough heat that it actually ignites the hydrogen gas it's producing. The lilac color of the flame is due to atomic emission from the potassium atoms. If we watch this in slow motion, we can see just how hot the potassium gets. It starts breaking up and spitting off little chunks. As it approaches the left edge of the beaker, there's enough excess hydrogen that it spontaneously ignites.